great. Great. Hello, welcome back, everyone. Today we are going to continue to talk about our bicomodules over comonoids in our category of polynomial functors. So let's see. Yeah, so we're going to start by kind of reviewing a little bit of what we talked about last time about these bicomodules, and I'll give sort of a different, slightly different perspective on how to think about these bicomodules, and we'll see that in some sense there is this correspondence between these bicomodules and a certain kind of pro-functor, which we'll get to when we talk about that. And then once we have this equivalence, we'll be able to show another equivalence where we can show that these bicomodules are actually going to be what are called parametric right adjoints between certain categories. And we'll see that correspondence as well. And then finally, we'll talk about how you can actually compose bicomodules together, but we'll get to that when we're there. Yeah. So let's start by thinking about, by reviewing sort of what we saw last time about these left comodules and right comodules. So we talked about, or David talked about last time, how a left C comodule is, you can think of it as a functor from the category C to the category poly. And what that does is for each, I've sort of like drawn maybe like one morphism from C so that we can see what's going on here. For each object in C, we assign to it a polynomial from poly. And so this is the polynomial with 1, 2, 3, 4, 5 positions, and then there's 3 directions on top of this position, 2 directions on top of this position, 2 directions here, 1 direction here, so on. And similarly, we've assigned another polynomial to this object C prime. We've given that a polynomial as well. But since we want a functor, we actually want every morphism in our category C to correspond to a morphism of polynomials. Now, our familiar sort of morphisms of polynomials, they are a function between the positions, forward along the positions, and then backwards between the directions. So for example, I've labeled these 1, 2, and 3 to indicate how this function maps over here. So this position is going to bring us to 2. This position is going to bring us here. This position here, and these two both over here. And then we have some map. I haven't actually drawn out the map, but we know that to give a full map of polynomials, we need to also say how, if we start at this position, that takes us to this position, and so how do these directions map back to these directions? And then how do these directions here map back to these directions here? And so on. So yeah, so that's how we can think of a functor from C to poly. But we can also break this up a bit and think about it from a slightly different perspective. So one thing we could do is just focus on the positions for now, right? If we have this functor from C to poly, but we only focus on the positions of the polynomial it gets sent to, we're sending each morphism to a function between sets, the position sets. So you can think of this just as a functor from C to set. And I've labeled this x. Let me draw this x a little bigger. So this is a functor that I've called x, and it's a functor from C to set. But then there's some more stuff going on with the directions, right? And so we can actually think of what's going on with the directions in a slightly different way than our on-directions maps here. So once we have this functor from C to set, let's look at each element of all of the sets that we're mapping to. And let's just draw out this map. So this 2, or this point here is mapping to 2 here, because I've labeled it with a 2. this is mapping to 1 here. I'm not going to draw all of these because it's going to clutter the diagram so much, but you can imagine an arrow from this one to the 2 here, and then arrows from each of these to the 3s there. And once you have these dots and these arrows, you can think of that as a category in and of itself, right? Where the objects of the category are the elements of all of these sets, all of the sets that get sent to by this functor x. And the morphisms of the category are basically these functions, but sort of like restricted to each of these individual elements of the set. And this is a construction that you may have seen before. We call this the category of elements of this particular functor. It's also, I guess, it's a specific example of the Grothendieck construction. We are going to denote this particular category by this, using this sort of integral symbol here. So we have this category integral x, which is just the category of elements of this functor interset of this functor x. Yeah, and so why do we care about this category? Well, I've already kind of given it away there, but we can now think of these on directions functions as, well, let's see. So we have, if we start here, if we start with this element, we need an on direction. Well, this maps over here, and so we need an on directions function from these over here to these. And so now this is just again, it's a function of sets. So we can think of these on directions functions as assigning each position here a set, and then, or each object here a set, and then for each of these arrows this way, we give an arrow backwards, we give a function backwards between these two sets. And that's just a functor from the category of elements of x op to set. And so we can break up any functor from C to poly as these two functors, one from C to set, take that functor, take its category of elements, op it, and then give another functor from there to set. So that's just another way we can think about these, and we'll see why this is a nice perspective in a second. But first, let's review again our right comodules. So a right D comodule, we saw last time, is just a bunch of functors from D to set. It's going to be one functor from D to set for every position of our polynomial, of our carrier polynomial P that carries the bimodule. Yeah, by the way, we can think of this, the entire polynomial P, as sort of, right, like we sent each of these objects C to some polynomial here, but if we add up all of those polynomials, that's the polynomial, the P here, that carries the whole bimodule, or the bicomodule. Now, a right D comodule is going to be a functor from D to set for each of these positions. And what are the elements of these sets? They're just the directions at that position. Here, for example, if we pick any one position, let's just start from the first one, we get a functor from D to set. Each object in D is going to give us a set of the directions. And so, for example, this object is going to give us this one direction here, and then maybe this object gives us these two directions here. And if D has more objects, then we need to assign each of those a disjoint set of directions at that position. And so we're essentially partitioning all of these directions and telling which object of D sends to that set, maps to that set. And then for any morphism in D, for example here, we get a function from here to here. So maybe this function assigns this over here, so this to that. And it's going to do that for every position. So we're going to have a function from here to here, a function from here to here, and so on for all of these, all of the possible positions of P. And that's our right D comodule. And so now I've drawn these together on the same polynomial because that's what our bicomodules look like. They're a left C comodule and a right D comodule that both use sort of the same carrier polynomial here. And so you can see already how these two are interacting with each other. But in order for our construction to be a bicomodule, we need one more condition, which is given by this commutative diagram here that David sort of highlighted last time. It's our only condition, right? Like everything else about this definition is just a left C comodule and a right D comodule. And then there's one condition that tells you how the right C comodule action is compatible with the left C comodule action. Sorry, right D and left C. And it turns out that if you translate this condition, I won't go through the details of how to translate it, but if you read off what this says here, it's actually saying that if you fix any D here, and then use the map here, use a map down here in C, well, so that's going to give us a, sorry, not a map down here in C. I actually want to say a map over here in our category of elements of X. If we look at this arrow, that's going to give a function from here to here. And what we're saying is that if we fix D, it's actually going to give everything that maps to D here. If we start here with something that maps to D, it's also going to map to something that maps to D here. Right? So again, right, we get some sort of on directions function from here to here. And what we're saying is that if we just restrict to everything that maps, that's given by the same object of D here, you still remain, you don't go up here, right? You're still going to stay in you're still going to get something that's mapped to by the same object of D. Okay, and so we get this nice sort of like grid-like thing where we have objects of this category of elements being each of our positions and telling us all of these directions. And then these objects of D are kind of partitioning all of our directions in a way that's compatible with the action of the left C comodule still. And what that gives us is actually going to be a functor. If we combine this functor from the category of elements of X up to set with this thing here, and since we know it's compatible, we end up with a functor from category of elements of X up times Z to set. I'm going to call this F. And this is a functor, but it's a special kind of functor called a pro-functor. It's a pro-functor between D and the category of elements of X. Right, so once we specify one object here, which is one of our positions, and one object here, we get some set here. And we can either kind of like jump around with the set. We get a function either by sort of adjusting with a morphism in D or by adjusting with a morphism in the category of elements of X. Okay. I'm going to pause there a little bit so you can digest this for questions. I'm going to get some water. Okay. Okay, so in summary, what we basically just showed is that you can think of a CD bicomodule as a functor. It's going to be a functor I'm going to call X from C to set. And then you take that functor and you look at its category of elements, and then you give another functor from that category of elements up times D to set. And that's just like this concise way of telling us what this bicomodule is. I said this was concise, but this is still not sort of maybe the nicest thing to be able to work with. It gives you a sense of kind of what's happening here. But I'm going to spend the next few minutes telling you how another perspective we can look at this particular construction. And this, by the way, all of this, at least, yeah, up to like 1 and 2 here, is due to Richard Garner. David mentioned he gave a talk in 2020, I believe. No, 2019. I think December of 2019 or something like that. And this was, right, so this result is from there. But I'm going to review it here. And yeah, so let's start by looking at how else we can interpret this f here, right? We have this functor from category of elements of x, op times d to set. You can curry this to get an equivalent functor. I'm still just going to call it f from category of elements op to the category of functors from d to set. These two things are equivalent. Now, if we have a kind of a functor like this, what we can do is we can take what's called the co-completion of this category, so we freely construct all of the colimits here, and what we're going to end up with is a functor from that category to the same category from d to set that preserves colimits. Now it turns out that the colimit, the co-completion of a category is just by the co-unate lemma, is just the category of functors from that category into set. And the way we think about this is that there is this there's this fully faithful embedding from this category op, to functors from that category to set, given by the Yoneda embedding. Everything else here is a colimit of these of the representables that are given by this embedding. And so we can think of any f is equivalently given by a functor, I'm going to call this f prime, by a functor from this this co-presheaf category on the category of elements of x to the co-presheaf category on D, such that it preserves colimits, right? It needs to preserve all colimits. It turns out a functor between presheaf categories that preserves all colimits is just a left adjoint. So functors from here to here are equivalent to left adjoints from here to here. Now, left adjoints from here to here are in turn equivalent to right adjoints from here to here. That's just how adjunctions work. So we get a functor back this way. Also, this one was f prime. Then let's just call this g. So we can think of this equivalently as, again, we still have this functor from C to set and a functor from the functor category between D to set to the category of functors from the category of elements of X to set that is a right adjoint. Right, so we have a right adjoint here. Now, let me just write this out again because, so we have a functor that looks like this. Now, it turns out that this particular category, when we take the co-presheaves on the category of elements of a co-presheaf, you can equivalently think of that as first a functor into set from the original category C. Remember, X was a functor from C to set. You first think of the functor from C to set, and then you give a natural transformation into the specific functor from C to set that is X. And you can work this out. This isn't too bad to work out, but you can see that like these, you can identify functors from category of elements of X to set with these functors from C to set equipped with a natural transformation into X. Basically, the natural transformation into X is going to tell you sort of how to like break up all of these sets so that like you figure out which one corresponds to like which object here. Okay. And now if we have, remember this is a right adjoint, so now we have this data, we have this functor X from C to set, and then we have a right adjoint from D comma set to C comma set sliced by X. And you can equivalently think of this as just a functor into C comma set, ignoring sort of what the arrow into X does. But then this is no longer going to be a right adjoint, and this is going to be this particular functor from D comma set to C comma set is what we call a parametric right adjoint. And the definition of a parametric right adjoint is exactly that. You can get it from a right adjoint into a slice category like this. Now, what's this doing? Well, let's look up here. So since this is a right adjoint, it's going to preserve limits. So for example, it's going to send the constant functor 1, which is the terminal object here, to the terminal object here. So it's going to send 1 to the terminal object here, which is actually, since everything is equipped with a natural transformation into X, it's just going to be X equipped with the identity natural transformation. That's the terminal object here. And so this functor here, if we forget about this, is just going to send 1 over to X. So you can see already, if X is not also 1, this isn't itself a right adjoint because it's not preserving our terminal objects. But it is a parametric right adjoint in the sense that it's like a right adjoint parameterized on this X. It turns out that you can show, since this preserves limits, this functor here is actually going to preserve connected limits. So even though it's not going to send the product of two things over here to that same product over here, it is going to send the product to a pullback because products here are just pullbacks here. So it's going to send a product here to a product here, which is just a pullback here. And so it turns out that this preserves, this preserves connected limits. And in fact, sort of just the same way any functor that preserves limits between pre-sheaf categories is a right adjoint, any functor that preserves connected limits between these pre-sheaf categories is a parametric right adjoint. So when we're working with functor categories of functors into set, these all sort of work conversely as well. Okay, so why do we care about this? Well, first of all, one thing, we've actually seen parametric right adjoints before. We've seen functors that preserve connected limits before. An example of this is just the polynomial functors P. And so, for example, we saw that polynomial functors actually preserve connected limits. And you can think of any polynomial functor P as a parametric right adjoint from set to set. And so here, basically, D is going to be the one object category. C is going to be the one object category with only the identity, which we can call, I think, by our polynomial notation, we call Y. And so polynomial functors are equivalent. What this equivalence tells us is that polynomial functors are just the y bicomodules, which is exactly what we would expect, because it turns out that this carrier will just be p, and there's no extra information here if these are both going to be y. But we can actually generalize this, and in some sense, a parametric right adjoint is just a generalization of our polynomials. Now, throughout this whole course, we haven't really talked about multivariate polynomial functors, which some people are interested in. And it turns out that the reason we haven't talked about it is because it just pops out of this theory as well. Because if we think about D and C here as discrete categories, what we get is let me write it up here. Can we still see here? Hopefully. Yeah, great. If we have write as capital P, a functor between Iy is our discrete category whose objects form the set I, into J Y set. Well, this is, we can think of this as, let's see. So first of all, we can think of this like functors from this discrete category jy into set as just a set sort of raised to the power of j. And so what this is, it's going to give us j many polynomials, but we actually have, instead of just one set, we're feeding it I many sets. So it's j many, let me just write this out, j many polynomials in I many variables. And so our parametric right adjoints between these functors from discrete categories into set are these multivariate polynomials, these j many polynomials in I many variables, and they are exactly the jy, comma, Iy bimodules. I'm just going to write, let's just write Q for now. Yeah, and so, right, so these are our multivariate polynomials. Okay, yeah. And finally, why do we care about this sort of notion of preserving connected limits? Or sorry, connected limits. It turns out that a functor, we briefly mentioned this towards, I think on day 2, and David can go into slightly more detail about this on our last day. But if we have a functor from, so we can think of functors from D to set as database instances on a database schema given by a category D. And what this functor does, we can think of it as a way of taking a database instance on some schema D and turning it into a database instance on some new schema C. And it's some way of transforming a particular set of data. And this particular transformation is the kind of transformation we want, in that it preserves connected limits, especially, namely pullbacks. It turns out that if we think about what pullbacks are here, they're basically just these, they're basically kind of, we can think of it kind of as like a type of query. And the fact that this functor preserves connected limits means that some sort of structure of this data is still going to be preserved. And yeah, and so David will go into this in more detail next time. But yeah, so we can call these parametric right adjoints data migration functors. And so it turns out that CD bicomodules are exactly these data migration functors. Okay, you can get some water. Let me know if you have any questions. So we've been writing this notation. Let's see. Actually, let's talk about this. Okay, so we have we know now that CD bicomodules are the same thing as these parametric right adjoints. I'm just going to write PRAs from D sets to C sets. Now, the thing about these, though, is that you can compose them. Because if you had another PRA from A set to D set, you could compose this one with this one, and, well, it turns out that the composite of two PRAs is still going to be a PRA, because it's still going to preserve connected limits. And so in some sense, well, this one is going to correspond to a DE bicomodule. And so there should be some way of composing a CD bicomodule with a DE bicomodule. Now, this might seem a little strange because so far we've been thinking of these as like objects rather than maps. Usually we compose maps. But maybe it's not so strange after all because we've been drawing these like this the whole time. Or David draws these like this. We have the CD bicomodule, and we have a DE bicomodule. So it does look like the notation we're using here suggests that there is somehow a way to compose these into a single CE bicomodule. And it turns out that there is a way to a composition law we can define on any bimodules or bicomodules in any monoidal category, as long as the monoidal product that we're using preserves equalizers. Now, the monoidal product we're using is composition, and it preserves all connected limits, so it does preserve equalizers. The reason why we want it to preserve equalizers is because this is going to be defined with an equalizer here. Let's see. So we're going to define the composite of these two bicomodules, and well, it's going to need, what it's going to need is it's going to need some sort of left C coaction and some right E coaction. Well, we know that P already has a left C coaction, and Q already has a right E coaction. And so if we take P compose Q, we can use sort of P's left coaction, or C's left coaction on P to get a map that way. And then, well, we have a map from Q to Q compose E, and so we can get another map this way. But this sort of like kind of doesn't acknowledge the fact that they also both have this sort of coaction going on with D here. And in fact, there's two ways D can interact with this. Either, so there's a map from P to P compose D, and then we just compose Q at the end, given by this. I'm going to try to write my rows with tails. This is the right coaction on P. But we could also have gotten from here to here by using the left coaction of D on Q, because there's a map from Q to DQ this way, lambda. And this lambda is for actually for this bicomodule, and this row is for this bicomodule. But hopefully that's not confusing. But in some sense, we don't want there to be sort of these two competing coactions with D. And so we take the equalizer, get some polynomial R, This is the equalizer of these two maps. And this is going to be our new carrier of our CE bicomodule. It needs a map into C compose R and a map into, well, let me not draw these yet because we don't know what these maps are going to be yet. A map into R compose D. But we know that our tensor product preserves equalizers. So we can compose this on the right with E and on the left with C to get these new equalizer diagrams that look like this. And let's see, it turns out that if we take this map, right, like this map here is going to make these commute, so this is the map keeping P and D the same, but taking Q to QE. Here it takes P to CP. And it turns out that this map here is going to let these two be the same map, and so there's going to be a map from R into this equalizer here. And similarly, there's going to be a map from R into this equalizer here. And these two maps are going to give us our bicomodule on R. And that's how we compose bicomodules. Now, this, it's kind of nice diagrammatically, but it's a pain to do actually in practice. And so, but what we hope is true is that this way of composing bicomodules that you can do in any sort of diagrammatically is actually going to coincide with our composition of parametric right adjoints. And it turns out that this is, in fact, the case. But it's a little hard to just sort of directly, this is kind of almost like too general of a case to like be easily able to grapple with. And so we're going to simplify this to the case where this second thing we're composing by is actually just going to be a single, let me grab a different color here. It's just going to be a single D set. Let's see. So, right, so instead of composing a functor from D set, let me draw it like this. So instead of a functor from D set to C set with some functor from E set to D set, we're just going to pick one D set. And it turns out that since functors are these functors are going to just be completely determined by where they send every D set, we only really need to worry about composition in this particular case. And it's maybe a little silly to call this composition. This is just applying this functor to one D set here. So let's call this D set Y, and this functor, this parametric right adjoint, F. And somehow this is we're going to say that F corresponds to a bicomodule, CD bicomodule carried by P. And then this, well, we know a 1 can also be thought of as 0, set. And so this is just a D0 bicomodule, which in fact we saw last time are just, D0 bicomodules are just functors from D to set. And so we have that correspondence. And what we want to show is that if we compose this the way we did down here, it's going to be the same, it's going to correspond, the parametric right adjoint it corresponds to is going to be the composite here. And I say the parametric right adjoint it corresponds to, but it should just be a C0. Since this is a C0 bicomodule, it should just correspond to a C set. And so the C set that this corresponds to is just F of y, f evaluated at y. Okay, so that's what we need to show that composition works the way we want it to. And let's see. And I'm not going to go through every detail of this, but I want to highlight some interesting parts of this. So first of all, I haven't written what set to put here. Now, if we remember our correspondence here, the set that goes here should be the sum of y evaluated on all of the possible objects of D. So I'm going to write this as y D with little d in this big D. Really, these are the objects of big D, so I should maybe write a 1 there. But this is actually also just the objects of our category of elements, right? Like you can also think of this as the objects of the category of elements with y. And in fact, right, so the positions are always going to be, the positions of our carrier are always going to be the objects of the category of elements of that one sort of functor, one functor from C to set that 1 over here maps to, according to our correspondence. Okay. So how are we going to do this? Well, let's see. So let's start by considering what this f, okay, actually, I called this f. I'm going to rename this because I actually wrote this differently in my notes. What do I want to call this? Sorry, I'm going to call this G. And now the core of our proof is we're going to go back. Remember, we got from bicomodules to these parametric right adjoints by way of these pro-functors. And so we already were pretty familiar with how to give a pro-functor from a bicomodule. And so let's take a look at how to get explicitly from a bicomodule can we actually give a formula for this particular parametric right adjoint evaluated at y. So what is g of y? Well, so we're starting with this. Let's say our bicomodule P corresponds to some, again, it's some functor from C to set along with some pro-functor from this op times D to set. Again, I'm actually going to think of this as just a functor into, by curring this, the comma set. And then we do this co-completion. And then we want the right adjoint of this. Now, it turns out that it is well known, and when I say well known, if you search up on the NLab page for the adjoint functor theorem, you can find this formula. The right adjoint for a left adjoint between, for a a co-limit preserving functor between two pre-sheaf categories is given by the following formula. I'm going to give you, other way. I'm going to give you the formula for the right adjoint G here. Now G is going to take some D set. We like our D set Y. And I need to give you back a functor from category of elements of X2 set. And what I'm going to give you, actually I'm going to call this G prime because this isn't quite our parametric right adjoint. Yeah, this is our right adjoint, and then we're going to turn it into a parametric right adjoint. Now, this is going to be, we need to give a functor from here to here. And so this is given by the set of natural transformations of two functors from D to set. One of them is this f here. Now, what do I mean by that? Well, this f here, if you plug in, if we, right, because this is going to be a functor from category of elements of x to set. I guess I'll just call this integral x to set. Now, this functor takes in some integral x and spits out a d set. So I'm just going to write it like that, because you can plug in our object of integral x into here to get a d set here, which is what you need for this Hom functor here. And then what we're going to Hom it with is just y, another d set that we have. Now why write this like that? OK. And so that turns out to be the formula for this right adjoint here. It's a really nice formula because it doesn't even need to use this f prime. We really only need to use what f prime is evaluated on the representables, which is actually already given to us by f. OK. Now, but this is this right adjoint from D set to integral x set. What we want is the parametric right adjoint that then takes this to C set, C comma set. That's not too bad. The way to get that is just to evaluate this on, given an object of C, evaluate this on every sort of object in the category of elements, so every element associated with C, and then multiplying all of those together. And so it turns out that this functor that we get, given this information, the corresponding parametric right adjoint is this functor from D comma set to C comma set that is going to send y to this product of, let's see, I'm just gonna write little I, but these are the, let's see, let me see. I don't want to, oh yes, I can write this like this. Right. No, I'm gonna leave this empty because this is where we plug in the object of C, and then just taking this and putting it here. So that's the set of natural transformations. Okay. Great. Okay. Now let's rewrite this in the language of, actually, let me see, 5 minutes. So let's, first of all, I wrote this as I in, actually, what do I want to do here? Let's see. Okay. So we've determined that the C set that we get by taking these two things, converting them to their corresponding parametric right adjoints, and composing them is this particular functor from C to set, where you plug in a C here, and then it gives you this product of all of these natural transformations. And this looks a little odd, but I will show that this is sort of exactly what you're going to get if you compose these as just bicomodules. Now, so we're going to need to use this limit diagram, but it turns out to compose these two bicomodules, but it turns out that things become a little easier if all of these d's are zeros, because, oh, well, we're going to replace all the c's with d's, I suppose, and then replace all the d's with zeros. And what you end up getting is a diagram that looks a little like this. Right, so we have our, right, oh yeah, so right, we're replacing all the e's with 0, sorry. Still the same C's and D's, but now E is 0. And this is just a set here. And so we have this C composed with P, composed with this particular set here. I'm just going to write this as sum of the functor y applied to each object in D. I guess I can write that. There's a map from, not S. Right? We actually don't have to worry about this bottom row anymore, because if E is 0, sorry, if Q is just a set, then this bottom row is just the exact same as this row here, because we're replacing Q with the set. So we only really care about this top part here. Let's see. So this looks like that. Okay. This looks a little complicated, but essentially the point is we take the equalizer of these two arrows to get some set here, and then similarly the equalizer of these two to get some set up here, and I'm just going to call this set. Just call this set S. And then this is a C coalgebra, and so it's going to be this. It's going to correspond to the functor, a functor from C to set. And we want to show that this, the functor corresponding to this, is actually this functor. And the one thing I want to point out here that should get you started on trying to check this correspondence is that the elements of this set here, well, this is the polynomial functor P composed with the elements of the functor Y. And what does that give us? Well, an element of this is going to be a pair, I comma, we call it I comma alpha, where I is just going to be, let's see, where I is a position of P, right? We specify a position of P. And then for each direction coming out of P, we specify an element of this. Now, each direction coming out of P, the directions coming out of P, according to our sort of pro-functor perspective here, the directions of P, remember, the positions of P are just the elements of this functor. It's the objects of this category of elements. But the directions are everything. It's going to be the objects of a different category of elements. It's going to be the one that if we pick the position, if we fix a position here, send it to a functor from D to set, it's going to be that, the objects of that category of elements. Those are our directions. You can check that from what we did earlier. And so this is going to be a functor from sort of the sum over F applied. Let's see, this is, I'm going to phrase this as a, let's phrase this as a functor. So, right, so we apply it to this I, but then we also apply it to every object D in big D. And that is the set of directions at this position I. And the directions, we send each direction to an element of this set here. And now what we're doing is we're sending the elements of this functor applied to both I and D over every D and D to the elements of this functor applied to every D and D. And it turns out that what this equalizer guarantees, so this equalizer is going to be all pairs that look like this, that satisfy the fact that like these two morphisms are going to send them to the same thing. And so you're going to get several equations out of this. One equation you're going to get out of this is that if you figure out where which element of D this part came from. It's going to be the same as the element of D that this part came from. And so really you can think of this instead as a bunch of functions, alpha sub D from f of I of D to yd. And I believe that is given by sort of the fact that these two morphisms send you the same thing up to here, sort of send you to the same object here up to here, or the same element. And then if you check that what it means for these two morphisms to be the same over here, the equation that it gives you is going to be exactly the naturality square given by the morphism of D given by over here. And so it's going to tell us that every naturality square that you can get commutes like so. And that is exactly what we need to say that an element of this equalizer set S is a position of P as well as a natural transformation from Fi to Y. And so it turns out that these two do give us the same thing through this kind of, admittedly, kind of long sort of argument. But it turns out that composition of bicomodules is the same thing as composition of these as functors. And so really these are the same category, the category of where the objects are categories and where the morphisms are these bicomodules between them can be thought is equivalent to the category of parametric right adjoints, where the objects are these co-presheaf categories. Morphisms are the functors between them. And that's it for today. Thank you. Feel free to ask any questions. And we will have one more class by David on Thursday.
Those are the ones that all.
Okay. Cool. I think we're probably good. Okay, I'm over here. Hopefully can you still hear? Okay. I'm reading these questions. So do the category of bicomodules and the category of PRA functors agree on the maps too? They're both natural transformation. Yes, that's a great question. So yeah, I didn't show this correspondence, but I believe it is, in fact, the case that morphisms, bicomodule morphisms, are also natural transformations between functors from C to set, right? And I believe this is actually a little easier to show than this. But it's a similar kind of argument. Where you notice that the data of a bicomodule morphism is actually going to give you a sort of, very similarly to this, it's going to give you some sort of like thing that could be a natural transformation, and you just check that the conditions actually do give you a natural transformation. Yeah, although it's easier to see the correspondence here, and then you have to check that the natural transformations of like these pro-functors are actually the natural transformations of these right adjoints, but I think there's a formal way to do that. Yeah, I think that was the question. And in fact, I believe David next class will talk about the pro-arrow equipment that this induces. And so that generalizes sort of all of this, yeah, all of this stuff, basically. I think that's it. Okay. Okay, cool. Thanks.